Welcome back, class, to the lecture on machine learning. Last time we discussed the logistic regression algorithm for machine learning, which is a classification technique. And before going to the lab side of that work, we will go and discuss a little bit deeper into another important topic, which is the problem of overfitting and regularization. So what is it? Let's see. So if you remember, initially in the first chapters we saw the housing problem, housing prices problem, which is a regression problem basically. And over there we saw that some data was given to us based on the historical records, and over there were the values given that mapped the size of the house to the price of that house. So we saw over there the data that is given to us, and we used different types of techniques to model our data. So we did the training part, and in the training what we do is that we take a type of model, for example a line, and try to best represent it, try to mm, try modify or tune its parameters so that this line best represents our model, our data. So we normally call this line over here, we call it our model. So this model can be different. For example, in this case, the data, if you see, if I'm going to use this line to represent this data, it will never give me a very good representation because the data is not linear. So we have seen this thing many times. So we discussed at that time that linear is maybe not a correct option for many types of data patterns. So remember, the whole story, the whole game is that you want to get some idea about the pattern that exists in the data. So what sort of pattern it is, you will try to represent it with the model that you select. So in this case the model was a linear model. Okay. And when you see, normally when your data is highly dimensional, you cannot plot that data, you cannot make a graph, and you cannot see the difference between the values and the line. Else, if it was always like this, then the life would have been much simpler. You take the data, you plot it, and you already know. So practically, data are highly dimensional. So they are not only two values in the x columns. There are many values, sometimes 10 columns, 20, or even 100 columns. So in that case, the data is high dimensional, and we cannot make a plot of that data. So we rely only on the numbers to tell us about the model if it represents the data. So for example, for this case, if you see this linear model, this line, it does not represent this data very well. So in that case, you all know what will happen. The error or the cost value will be high. No matter what you do, the cost will be high. So more you will try to put this data to tune this line, it will never give you a very good answer because there is no good answer at all. It does not exist. No matter what type of slope you choose for the line, it will never give you a perfect or a very good answer. So practically when you will try, for example, the gradient descent on a linear model for this data, after the time passes, it will try to converge, but the convergence will be on a value of j, or a cost that will come out. It will be not so low, it will be high. So such a problem normally where your training does not give you a good result on your model, or you can say your model does not represent your data properly for any reason. There can be many reasons. This type of problem we normally call it underfitting. Okay, underfit. Your model is not fitting properly. Okay, So this is the first case. This is the one typical problem that occurs in the machine learning problems. So it's not such an easy job that you are given with the data and you just decide for a model and you train the model and then that's done, it's finished. No. So there are many hurdles, as this is the famous proverb, devil lies in the details. Details, they are devilish. They are very cumbersome. They make big problems. On theory, things look simple, but when you go into details, they become more and more complex. So this is the first problem you saw over here, which is underfitting. Another problem that occurs is that, for example, if you remember at that time when we discussed linear regression, and we said that you can, for example, use higher order terms. So for example, you have theta 0 plus theta 1 x 1, and then I told you that maybe you use some higher order, so maybe I have theta 2 x 2, and then you use some higher order terms. Higher order means they have higher the degree term over here is higher. So for example, you use another term which is x1 square, or another term you use. So thetas are constants or tunable parameters. So we don't care about them, but the x values, the inputs, they are over here increasing. So you see over here. So initially they were first order polynomials, now they are second order. So x1 square, x2 square. So when you see these quadratic terms, what they will do? So definitely what they will do, we have seen it at that time in the chapter, that this line is this equation is no more linear because of these two. These are not linear. So as you add up these terms, this term, such terms, your line will become more and more complex. Your function will become more and more complex. So don't call it line because it's no more linear. Okay. So it will become complex more and more. So what happens? It will be representing your data like this, for example. It will trying to match every possible point as closely as possible. Okay. So what's bad about it? So it's good. When your data is, when your model is matching the data very closely, what does it mean? Your j will become almost close to 0. Okay, so it will try to be as close as possible to 0. The training cost over the training data, your model will be performing very well. But the problem that lies, for training it's okay, it's perfect, it's good. But the problem will come when you go and you try to test your, try to evaluate your test data. So remember, at that time we saw that train test split function of sklearn. So for example, we saw, so normal, I think it is 75% normal split. If you don't give any value yourself, it is 75% and 25%. Okay, so 75% of the data is automatically your training data and 25% remaining is your test data. So what happens is that this test data, why you make it? You want to use it later to evaluate your algorithm, your model. Okay, so training data is used to train your model, whereas the test data is used to evaluate how good this model is. But in this case, what will happen is that your model, it will perform very well on training data and your error will be almost 0 on training data. Okay, but on the test data, what will happen? J will be too big, too big. Why it will be big? Because for example, here so the lines you see over here, let me choose another color. So let's say, yeah, this yellow color. So when the data will come and you have to predict over here. So you see over here this model, it is very erroneous. It's not so good. Why it's erroneous? You can see over here, for example, you have got a very small house. So this is not a good color. So which color should I be using? So it's a very small house over here, but suddenly you see over here, because it is overfitting, for one particular example, maybe there was some example in your training set for any reason. There was one such example where the small house was sold for more high price. But it's not a general rule. It should not be done for all the future houses with small sizes. They shouldn't be sold higher. Remember, the the model, it should be trained for the general data. It should not be trained on specific examples. So this type of things that you see, it will give you so much mistakes on the training data, because your model has trained itself, your model is closely following the training part of the data. So it will not generalize very well. So the word that is most commonly used for this thing is that your model is not generalizing. Generalize means that it does not look overall pattern. It is trying to follow too much to the specific problems, specific examples. Okay. So here you see what is happening is that this model is very curvy, and you see over here, for example, another big problem that for some reason one house which was very big in size, it was sold for a lower price, and now you see your model over here, it is following that trend, and all the future size bigger size houses, they are being sold, they are shown that they will have less price, which is not correct. So overfitting is generally very bad. It is because your model is not generalizing properly about your data, and it is trying to follow every single example of data, every single example of the house that was sold, and it's trying to follow that. So it's not overall capturing the general pattern in the data. So this is overfitting, it is bad. The other side you saw, which was underfitting, that is also bad. Underfitting is a problem that comes, that is the first one you will see, because remember, your data has two parts, training and test part, and underfitting is the part that you will see in the training data. When you are training your model, even on your training part, your model will behave badly. So on your training data, the model is giving you bad results. For example, a typical example is that on training data, you get an accuracy of 70%. So most cases, it depends also on the type of the problem. Okay. So 70% is not good in most cases. Okay. So when this occurs, you know that you are underfitting your data. Another name for underfitting, we call it high bias. High bias. High bias means that basically you are training data, the data that is in your training, your model is not able to capture the trends in the data correctly. Whereas when the training becomes good, for example, you on the training data, you change your model and it becomes, for example, 98% or 99%, then you move to the next phase, you apply the test data. When you apply the test data, now you see something strange, that in the training you had 98% accuracy. So this percentage that I show, this is for the accuracy. You remember we tested, used it. So on the test data you apply and you suddenly get 65% accuracy. When you see such a result, that training is very high, in test is very low. When you see such a thing, it clearly means that you are overfitting your data. Your model, it is closely following the training data. It's very closely following the training data, and it is not capturing the general trend in the data. So when the test data comes, for example, it will be giving wrong values for that data, wrong output for that data. So this is the problem. This is one of the main reasons that we do the train test split. Train test split, one of the main reason is you want to check if your model is overfitting. Okay, so these are the two extremes. In between these two extreme is your correct model with the correct parameter settings. So with the right choice of parameter settings, you will get your model just rightly tuned. So its tuning is done so perfectly that it's trying to represent the data as perfectly as possible. So between high bias and high variance, so overfitting we also call it high variance, and high variance occurs because your data, you get problems with the test data, not the training data. Okay, so between high bias and high variance, you get your just correct model representation. Clear? So why it happens? Remember, high bias or underfitting occurs because your model, it is not good enough that it can represent the data. So for example, it is lacking the flexibility. Just like for example, it is a straight line and your data pattern is not, it cannot be represented by a straight line. So in that case, that is high bias or underfitting. There is no other solution. You can never use a line to represent the data. There is no solution. You have to do something else. So in this case, what you can do is that you introduce some higher order terms in your data. Okay, so you introduce some higher order terms. So x square, for example, x cube, x power 4, these polynomial degree terms. When you introduce these terms, your function, it will become more complex, no more a straight line. And when it becomes complex, in that time, remember that it will possibly catch the overfitting. It will now it will get the problem of overfitting. So underfitting and overfitting, in between somewhere you have the just right combination. So how to find this combination? That's a big question. The best method is that you have, if you have the overfitting, okay, if there is underfitting, try to add more features. So try to add more features over here, and possibly features that are not linear. Try to add higher degree features. So for example, x square, x cube. Okay, so that is the solution to high bias, to add more features. Okay, but if you are suffering from high variance or overfitting, in that case what you can do to reduce the overfitting is try to remove the higher order features. The more higher order features you are removing, your line or your function will become more simple, and it will become slowly, it will be representing, it will become more simple and quite closer to linear function. So for example, you removed these two higher order terms and your function will become this quadratic equation which may represent your data perfectly. So you will keep on trying these things. So remember, machine learning, it is basically learning from the data, and it is an iterative or repetitive task. Remember, okay? So there is one repetition that occurs in gradient descent. Gradient descent itself is a repetitive task. You repeat, you do a loop until you converge. and there is another outer loop. So there is one loop of for gradient descent, there is another outer loop where you try or experiment with the terms. So the input terms or input variables you use in your model that you feed to your model. So if the number of terms are less, maybe you will have underfitting. If your number of terms are high, maybe you will suffer from overfitting. So first thing to check in any model evaluation is you check for underfitting. If there is no underfitting, then you go on, you try your test data, and if there is overfitting, you try to reduce number of equations, number of terms, not equation, sorry, number of terms in this equation. Okay, so these terms you reduce one by one, and hopefully somewhere in the middle you will slowly adjust on the just right choice. Okay, so that's the whole story between overfitting and underfitting. You get your best answer, and this thing is not only for regression, this is the same story that also comes for the classification problems. So remember, the most important point is that this just right option, because remember, now you can see over here your data, you can plot it, but I told you many times, if your data has many variables, many dimensions, you cannot plot it. So all these things that you see over here, this is just to train you, for example. So we are only using 2 parameters. Practically you will have many parameters, but the important thing is that your data, you have to try to choose the model that closely resembles the data. Okay, you can do it maybe in the first attempt by chance. Okay, or you can do it by mistakes and trying to correct the mistakes, which is called the hit and trial method. You try something, you make a mistake, you try to change, you make some improvements, and you keep on doing until you become very good or perfect. So this is what happens over here. 3 types of models: just right, underfitting, overfitting, and another name for them is high bias and high variance options. Okay, go through it, pause the video, just try to grasp these concepts before we go for the next slide. So remember, overfitting, it occurs if we have too many features and the learned hypothesis or the model. So hypothesis H is basically our model, okay, the equation that we use. So for example, this over here is the hypothesis, and we, with the help of training data, we try to choose these values for theta 0, theta 1, theta 2. We try to tune these values with the past data. So the learned hypothesis may fit the training set very well. Okay, so the J value is almost 0, but it fails to generalize to the new examples. So predict prices on the new examples, it is very bad. So it occurs because there is overfitting. Here is an example for classification, that was regression. Classification has also same problems. So here you see an example from the cancer data set. So in this data set, you can see over here the problem. You have got 2 features from the data, 2 input features, x1 and x2. If you remember the cancer data set we plotted, these can be one of those so many columns. So let's say there are 2 columns, x1, x2. You plot them and you get a graph like this. So you can see over here the red cross and the blue circles, these classes, they are somewhat mixing. There is no perfect dividing line between these 2 classes. Okay, so one bad example of classification is that you use a single linear line, so you use a linear equation. So you use a line to classify these two classes, to divide these two classes. Dividing them by a line is a very bad option because it's not possible. You will definitely get a very high error, or cost function value. Okay. So here you see this as a linear function that we are using over here, and this is the problem of underfitting. On the other extreme, in the case of overfitting, when we add more and more higher degree polynomial terms in our model or hypothesis function, because of these higher degree terms, uh, the line will try to, so after the gradient descent, when you have found the values of thetas, all those parameters, your line will be trying to perfectly classify the good and bad class elements. So it will trying to perfectly separate class 1 from class 2. And this is not a good approach. This is not correct approach, because practically there are always some problems that occur with the data. There are some special cases always over there. We never want to those special cases to affect overall interpretation we get from the data patterns. So this is an example of overfitting that's occurring, and somewhere between the underfitting and overfitting we have our perfect example where our model is perfectly classifying the two categories. So this is what the middle one is, what we want to do. So over here you see from those higher order terms, many higher order terms in the overfitting example, we remove some of the examples or many of the examples and try to make it simple, and with that we get good results. So we never know how the good result will come. Okay, only it can come what we know till now. We will see the techniques in the future. Only what we know is that going from overfitting to underfitting, we can go by removing the higher order terms. You can remove one by one. So as you are removing the higher order terms, your data will become more, and your model will become more and more simple. And when it's becoming more simple, it will go to the underfitting side. Okay. So you have to stop somewhere in between the overfitting and underfitting, somewhere where you get the perfect representation for your data. Okay. So here you see this was our example. If you remember, the same example of the housing price prediction. And you see over here we can have many features. For now, just for the sake of simplicity, we only choose two examples, two input parameters. So the x values we choose the size of the house, only one, sorry. So one input we choose and the output is the price of the house. There can be many other parameters. Okay. So when you will increase the number of parameters, so you see over here we can have maybe 100 parameters. Size of the house, number of bedrooms, number of floors, number of washrooms, how old the house is, what is the size of the kitchen. You can have many parameters, even tens or hundreds of parameters. Okay. So how much you will use, that will decide if you are overfitting. So normally overfitting will never come with only one parameter. The diagram over here that's shown, this is quite misleading. With only one parameter, I don't think that you will ever get a curve like this. Okay. So what are the options to avoid overfitting? Okay, for underfitting, you add new features. For overfitting, the opposite. You reduce the number of features. Okay, decrease the number of features. So what you can do is that you manually select the features which you will keep and which you will discard or remove. Okay. So for example, you have the feature size of the house, And another feature you have introduced yourself, which is size of the house square. So maybe try to remove this size of house square. Okay. And another thing that comes is that will definitely affect is the model that you use for your algorithm. Okay, for your overall system or machine learning model, what type of algorithm you are using. So is it a linear model you use, or is it a quadratic, or even higher order term? So if you are using, for example, a quadratic or even higher order terms, so for example, degree, you are using an equation which has degree 4 polynomials. Okay, so maybe your model is overfitting. Maybe don't use degree 4 polynomial. So it means the same thing that I have repeated so many times before. Don't use degree 4 polynomial, use quadratic or linear. It means reduce the number of terms in the equation. So if you see, same thing here, number of terms that are over there, cancel them, these extra terms. If you cancel them out, you remove them out, your model will become simple. That's what is happening over here. So model selection algorithm or the number of features. So it's almost same thing over here that's happening. So model selection means that, for example, you can use linear or quadratic models. Another thing that can be done to address the overfitting, it is called regularization. Okay. So regularization is something very interesting. So regularization is something that will do the same thing that I suggested over here. So for example, you have overfitting. Okay. So in the case of overfitting, what I suggested is that from overfitting you can go to underfitting side by removing these terms. Okay. So regularization is a process where you try to multiply these higher order terms with a very small value. Okay. So for example, if you have this term, if you multiply it with a very small number 0.001, what will happen? Effectively, when you multiply it with a very small number or a constant, you are almost trying to remove the effect of this term in the whole equation. That is what regularization does. Regularization will try to remove the effect of higher order terms in the equation. So you don't have to practically isolate and remove the terms yourself. You don't have to do anything because you don't know which one you should remove. Should you remove the term with theta 6 or the one that comes with theta 4? You don't know. Which one will give you best result? You don't know. So it's better let the computer do this job. It will do this with the help of regularization. So this is the theory that regularization, what we want to do is we keep all the features, all those parameters, but reduce or the magnitude or the value of those parameters. Okay. So that's what, if you have one term theta 6, try to multiply it with a very small value, and by doing this you reduce the effect of that term in the overall equation. So this approach, regularization, it works very well when you have lots of features. Remember, we are talking about over here maybe 20 or 50 or 100 features in a model. So when you have lots of features, each of which is contributing a little bit to predict y. So by this approach, what you will do is that you will try to ignore or neglect those features that have higher order terms, that make the model complex. Okay. So pause over here, think over it, go through this video. I suggest at least 1 or 2 times. Go back and go through these concepts again, and then we go next. So in the case of regularization, how the cost function works. So here you see. So this is the same thing we have seen earlier. This is your just fit example where you are using a quadratic equation, okay? Whereas in the case of another overfitting example, you are using higher order terms, and these higher order terms, they make the equation overall very complex, okay? So what we can do is that just imagine, just suppose that we penalize and make the theta 3 and theta 4 very small, okay? So when you try to make the theta 3 and theta 4 very small, in that case what will happen is that theta 3 multiplied by this x3, it will become very small because theta 3 is very small. Same is the case for theta 4. So when we make this theta 3 and theta 4 practically very small, close to 0, it means that practically we are making these terms 0. Okay. So how we do this? We will do this by adding a term inside our cost function, which we call as the regularization terms. So small values for these parameters, for example theta 0, theta 1 until theta n, when we choose the smaller parameter values for some of the higher order terms, it will make overall our hypothesis simple. How come simple? Here, this is our hypothesis function, yes? If I am ignoring these higher order terms, my equation is becoming simple. So same is the thing they say over there. So hypothesis simple means equation becomes simple. Okay. So simple small values for parameters will make the hypothesis simpler, and there will be less chances of overfitting. Simpler equations have less chance to overfit. Okay. So in the case of housing prices, you have for example 100 features. Okay. So you have 100 features, for example. So 100 features, they will have their own parameters. So there will be, for example, 101 parameters, not 100. Why? Because features you see, they start, for example, x1, x2 until x100. Whereas your parameters will be x1, x2 or x100, but there will be one more parameter if you remember, x0. Sorry, theta 0, theta 1 until theta 100, but there will be theta 0, which is the bias term. So theta 0 is your bias term, whereas theta 1 until theta 100, they are the terms, they are the parameters that are multiplied with x1 until x100. Okay. So what you do is that instead of theta 0, so you don't disturb theta 0. Theta 0 is the bias term. It is not multiplied with any variable, so you leave it alone. Don't disturb it. Okay. For other than theta 0, all other terms, theta 1 until theta 100, because they multiply with the different input values, so what you do is that you take those theta terms and you put over here the theta terms you put over here inside your cost function. So this is your cost function. You remember J equal to 1 over 2m, and this is your sum of errors, sum of square of errors. So this is error square, you sum it. You add over here another term which is lambda sum of theta square. So what does it do? Theta square, what it does is that theta is the one that is multiplying with the input x. Okay. So if some term x is complex, for example theta 100, it is being multiplied with so for example theta 100, it is multiplied with x to power 4. Okay, now it is a complex term. Okay, so it's a polynomial term, x to power 4 it makes overall the model or the function more curvy or uh, uh, more, you can say, it behaves not like a straight line. Okay, so it's a complex shape. So what can happen is that when you add the theta over here as a regularization term, what happens after each gradient descent, automatically this theta will be reduced because of this term is increasing the cost, so automatically this theta will be reduced. So gradient descent will automatically reduce it because over here you have put an extra term, which is the regularization term. So you put over here one term where you have theta square. So whatever is the value of theta, just square it. Okay, and then you take the sum of those values. So in this regularization term, you have got one lambda. Lambda is again, it is just same as alpha. So if you remember, there was an alpha which was called learning rate. Over here we have got uh, lambda, which is our regularization parameter. So here it is. You see the equation. So in this equation, you see this is over here lambda theta, sum of theta square. This is our regularization term, and lambda is the regularization parameter. So what will happen is that when you introduce this term inside your data, what happens is that slowly with each gradient descent, automatically your theta, remember, after every iteration of the gradient descent, your theta values change. But because of this term over here, your theta will reduce for some of the terms in the overall hypothesis equation. Theta will reduce such that your blue line will become more smooth like the pink line. Okay, so it will try to reduce, for example, theta of 3, theta 4, and it will keep the simple ones like theta 1, theta 2. Okay, so this is the regularization. And here you see in the regularized linear regression, what we do is that we choose the theta to minimize. So what what the focus we have is that our theta should be minimum. Okay, the theta value should not go too much high. So if lambda is extremely large, so same question as you have seen previously for the case of alpha learning rate. Here, if the lambda is very large, what will happen? If it's extremely large value, then what will happen is that it will try to cancel out most of the terms. So theta 4 will become 0, theta 3 will be 0, theta 1 will be 0, theta 2 will be 0, and only one term that is not affected by regularization will remain, which is theta 0. Remember? So for example, if theta 0 is equal to 5, so it will become a straight line which will cut the y-axis. Remember, theta 0 is y-intercept, so it's the intercept, so it will cut the y-axis at 0.5. So the more regularization, for example, you increase, you put a very big value, so it will become, the model or equation will become simpler, and in the end it will become a straight line, which you never want to do. So it is definitely going to be an underfit. So if you increase, so an exam question can be, if you increase or if you put a very high value for lambda, it will cancel out most of the higher order terms. Okay, most of the higher order terms will be cancelled out, and at the end, when the alpha is extremely large, then at the end you will only have one term left, which is theta 0. So in that case, your hypothesis will be equal to h equal to theta 0, which is the worst case and which is the example of high underfitting. Okay, So regularized linear regression, let's take a break and then we will come back to this, and also we will discuss the regularization in classification problems.